In this video, we'll derive the sampling distribution for a sample mean x bar. We're going to use this sampling distribution for the sample mean x bar whenever we're conducting inference for a population mean mu. The data in situations like this will be quantitative. We have to assume a few things. First, that the data come from a properly randomized design. Secondly, that the sample observations are independent. And third, the sampling distribution is normally distributed. Now, we can verify that these assumptions are warranted by checking these conditions. First, the data come from a random sample or random assignment to treatments in an experiment. That takes care of the properly randomized design assumption. And we have control over that. Secondly, the population is at least 10 times as large as the sample. That would give us independence in our sample observations. So this is an independence condition. And this is something we as researchers can control too. We can make our samples so that they're less than 10 times the sample size. And then thirdly, the population is normally distributed, which we don't have any control over, or the sample size is large, which we do have some control over if we're doing the research. Either of these conditions would be sufficient to make the sampling distribution of x bar normally distributed. Now we're going to start with this idea that we have a large population and we have a quantitative variable of interest that has a mean mu and a standard deviation sigma. So this is a population mean and a population standard deviation for this variable. And we draw an SRS of size n, and then we're going to have sample observations that we measure, x1, x2, x3, and so on up to xn. Each of these sample observations is a random variable. Each one comes from a distribution with a mean mu and a standard deviation sigma. So they all have that mean, each of those random variables. The sample mean x bar is a linear combination of these things. We just add them all up and divide by n. And so when we add up those n random variables that all have the same mean and the same standard deviation, and which are independent, we can figure out how x bar is distributed based on that. Okay, first off, the center. The mean of x bar is the mean of this expression, which is equal to x bar. It's x1 plus x2 plus x3 plus, and so on up to xn, all divided by n. To find the mean of that expression right there, we just add up their separate means. The mean of x1 plus the mean of x2 plus the mean of x3, and so on up to the mean of xn. And then we divide the sum of those means by n. Well, all those means are the same. They're all equal to the population mean mu. And we have n of them. So that sum right there can be simplified down to n times mu. And we're going to divide that n times mu by n. And when we do that, the n's cancel out and we wind up with mu. Well, that's nice. The sampling distribution of x bar is going to have a mean that is equal to the true population mean. And that means that x bar is an unbiased estimator of the population mean mu. Next, let's look at the spread. We need our rules for variances here. The variance of x bar is the variance of this expression that we use to generate x bar. It's just a linear combination of n random variables, all divided by n. And then we can take each of our separate variances for x1, x2, x3 up to xn, and we're going to have to divide by n squared because we have n inside here. When you make the variance of that, you have to divide by n squared. So we're going to have all these variances, they're all alike. They're equal to the population variance, sigma squared, and we have n of them. So we have n times sigma squared, and that replaces that long sum right there. And then we divide that n sigma squared by n squared, and some of the n's cancel out. We have sigma squared, the population variance, divided by n, the sample size. And then to find the sample standard deviation, the standard deviation of the sampling distribution of x bar, sigma of x bar, we just take the square root of that expression. And the square root of sigma squared is sigma, square root of n is the square root of n. So we have sigma over the square root of n after we take the square root. And this gives us a measure of the sampling variability of x bar. It depends on the sample size n. It doesn't depend on the population size. There's nothing in this expression that says anything about the population size. Sigma of x bar varies inversely with the square root of n, and you can reduce the sampling variability of x bar by increasing n. Just remember that there's a trade-off there. Bigger samples cost more money and resources, so you're going to have to find a balance when you're increasing your sample size. You just don't usually have unlimited resources to do that. Now, third, we got to talk about the shape of the distribution of x bar, this sampling distribution. If the population is normally distributed, then x bar is just a linear combination of n independent normal random variables. And so x bar is also going to be a normal random variable. That'll be normally distributed. If the population is not normally distributed, but the sample size is large, then x bar will still be approximately normally distributed according to the central limit theorem. So in sum, it comes down to this. X bar is going to be normal unless the population is not normal and the sample size is small. If you have a normal population or a large sample, then x bar is going to be normally distributed, at least approximately, and you'll be able to answer questions using that normal distribution. So here's a summary of everything that we know about the sampling distribution of x bar. It's a normal curve. It has a mean equal to the population mean. So the mean of x bar is equal to the population mean mu. The standard deviation of x bar is the population standard deviation divided by the square root of the sample size. So this pretty much sums it up. X bar is normally distributed with a mean of mu and a standard deviation of sigma over the square root of n if the conditions 1 to 3 above are met. That is, we have properly randomized design, we have a population that's at least 10 times the sample size, and we either have a normal population or a large sample.